I welcome you to the third lecture of the series of lectures on advanced computer architecture. Today, after having a review of what we have been talking in first two lectures, I will continue with the concepts of quantitative design of a microprocessor as well as the computing system. However, today we will give more emphasis onto the performance of input-output devices and input-output system when it is interfaced with the microprocessor. We will also talk about some laws and principles which governs and determine the overall performance of a system. Then, after about 20 to 30 minutes, then we will move on to the discussion on a well-known law for the enhancement of performance, and we will see how you can improve the performance of a system by making small improvements in certain parts of the system instead of making changes or improvements in almost all parts of the system. So, first of all, let us have a recap of what we discussed in first two lectures. You can see from this slide that first of all we talked about the computer architecture versus organization. So here we discussed that computer architecture is something which deals with the programmer's perspective, and the architecture of the family of processors is the same, whereas the organization of different parts of the system for different members of the same family may be different. Then we discussed about the technology trends and developments in the electronics technology, starting from the vacuum tubes and up to the medium scale, small scale integration, then medium scale integration, then large scale integration, and then presently we are in the era of very large scale and ultra large scale integration. So these technology trends basically gave rise to the enhancement in the performance of the system as well as reduction in the cost of the system. Then we discussed in details the design cycle, where in the design cycle we said that we studied how the performance is measured as well as how it is affected or controlled by the technology trends. And then in this case we also said that the technology gave rise to the enhancement in the performance of a system. And then we also talked about how the cost is determined and what is the difference between cost and price of a system. Then at the end we combined all these concepts, and then we discussed the relationship between the time, cost, and performance. Then in the second lecture, we gave emphasis onto the measurement of the performance. So first we defined the performance, wherein we studied that in fact time is the key parameter for the measurement of the performance, but at the same time the throughput of the system is also very important in a different perspective. For example, we said that for a single user the time is the only parameter, whereas for a design center or for a computer-centered manager, the throughput of the system is very important. So after making these discussions, then we talked about the price performance design, we discussed what is the relationship between cost and price, and we found that it is a very complex relationship, and with the increased enhancement in the performance, we have to have some increase in the cost, but we can compensate for this by increasing the volume, and we can reduce the list price of the system. However, after making this discussion, then we talked about the growth in the performance of a processor, and we said that how the performance have been improving from time to time when the new technology was introduced, and this way the new trends in fact enhance the overall performance of the system. Then we also discussed certain methods whereby we can find out the performance of the system, and for this we talked about the benchmarks. Benchmarks are basically the programs which are developed to evaluate the performance of a system vis-a-vis the performance of a standard system or in order to execute that particular program. We also talked about what are different types of programs which can be used as the benchmarks. Having made this discussion, we in fact concluded the last discussion by what are the basic and important aspects based on which we can have a quantitative design of a processing system. However, continuing with our previous discussion, today we will discuss how the performance of an input-output system affects the overall performance of a system. For this purpose, we will first be talking about the basic concepts which are used to measure the performance of an input-output system. You can see that producer-server model. What is a producer? Producer is basically the device that generates input to the system, which is to be serviced by the system. Whereas in order to connect the request from a producer to the server, which is a device that performs the requested service, we have to have a buffer in between the producer and the server, where buffer is in fact a storage which is working on the principle of a queue, which is first in, first out memory. A queue, as you people know, that queue is working on the principle of first in, first out. That is, any information which entered into the queue, that is serviced first, or any request which is generated first and placed in the queue, that will be serviced first and then it will be out. So, however, while talking about the computer's I/O system performance, the measurement of response time is very important. Response time is basically the time which is taken from the moment a request is placed in the queue and the time which is when it is finished, when it has been serviced by the server. So this way, the overall response time of the I/O system, it depends upon when a particular service request has been placed in the queue and when the server finished that particular service. So, considering this particular model of the system, we can talk about the I/O performance parameters. So, in this particular case, the basic principles which determines or which can be used to measure the performance of a system, the basic parameters are the diversity, the capacity, the latency, and the bandwidth. You can see it from here that diversity means that which particular I/O device can be connected to a system. So this actually means that depending upon the design of a particular system and the design of different devices, we have to find out what are different types of devices which can be connected. Whether a device such as, say, whether a system allows to connect a printer or not, whether a system allows to connect a CD-ROM or not, or whether a system allows to connect, whether it has got a USB port, and can we connect a USB port, a USB device to a system. So this means, this is what do we mean by diversity, that which particular device can be connected to the CPU. Capacity deals with the number of different types of devices which can be connected to a system at a time. So, for example, a system may allow only 3 different types of devices. So if it has got only one parallel port, so this means one device, either a printer or a corresponding some parallel printer port device can be connected. If it has got only one USB port, this means that it has got the capacity of accepting only one USB device, which may be a USB small flash drive, or it may be your printer, or it may be your keyboard. So depending upon what is the total number of USB ports available, we determine the capacity of the system. The other important parameter is the latency, which is the overall response time to complete a task. So it is basically the total time starting from the initiation of the request up to the completion of the service of for that particular request. So this is what is known as the latency of the system. The fourth important parameter is known as the bandwidth. Bandwidth is basically, it is something which is related with the throughput. So this is number of tasks which can be completed in a specified time. So this means in the presence of the restrictions or the characteristics of certain types of devices, some device may take longer time as compared to the other device. Then when we have to calculate the overall response of the system, overall bandwidth is determined what is the throughput of the system. That is, how many tasks can be serviced by a particular system in a specified time. So this is one thing which is very important in order to study the overall performance of a system with reference to the input-output devices. With reference to the input-output devices, the other most important aspect which is to be taken into consideration is the transaction time. Transaction time is the interaction or transaction time of a computer, and this time is in fact the sum of 3 different times. That is the entry time, the system response time, and the last one is the think time. The entry time, as it is very clear from its name, is the time for the user to enter the command. For example, if user is entering a command through a file which is having a list of instructions, then it may take only a few milliseconds to enter the command. Whereas if user has to enter this command from the keyboard, it may require some large number of seconds or time to enter the command. For example, a keyboard entry may be possible in 4 seconds or 5 seconds or 10 seconds. Whereas the entry or reading a command from a file, it may take a few milliseconds or a few microseconds, depending upon what is the requirement to access a particular file and what particular features are available in the system. Similarly, the response time is the time between when user enters the command and when the system responds. That is, if I enter the command now, after how much time will respond to this and it will give the result. This includes basically the time which is taken from the placement of the request in the queue to the response which is produced by the server. So this is the system response time. The last type of time is very important, and it may vary from application to application or from user to user. And this time is known as the think time. The time from reception of the command until the user enters the next command. So, for example, if user has entered one command, then he may need to wait till its response is available, or he may be busy in doing something else, and one may like to have a cup of tea also during this time, and during that time the user may be thinking. So this whole comes out to be in the category of the think time. However, when user is not entering any command, there is nothing available to the system to execute, the time may be going wasted. But for the overall system, this is the think time is also important, and that is in fact the time which is utilized by the system. It may have not been utilized by the processor, or it may not have been utilized by the I/O system or I/O devices or something else, but it all includes in this. The relationship between the response time and the throughput. You can see this thing from this graph, which is quite clear over here. Here you can see that this graph shows that the minimum response time achieves only 10% of the throughput, whereas the response time of 100% throughput takes 7 to 8 times the minimum response time. This you can see that is the total time which is shown over here at the top, which is approximately 170. It has got 170 millisecond, whereas the lower one is starting from 20 millisecond. The gap in between 20 millisecond and 170 millisecond is 6 to 7 times the total time. Whereas the knee over here, as you can see from this curve, the knee of the curve is the area where a little more throughput result in much longer response time is available. And this you can see that is the gap between 40% to 80%. The time requirement is small, the response time is small, but the throughput is large as compared to the overall time. So this is in fact the knee area, which is very important, and it shows that the performance here is much better as compared to the performance at the edges. So with this much introduction to the relationship between the response time and the throughput, now let us see that how we can calculate the response time and the throughput. For this purpose, we have to consider this black box model of the system, where we can see that system is assumed to be a black box and system is assumed to be in the steady state. Then some request arrives and that request departs. As you can see from here, from this diagram shown here as in the form of a black box, if the system is in steady state, then the number of tasks entering the system must be equal to the number of tasks leaving the system. We can define the stability of the system. A system can be said to be in a steady state if the number of tasks which arrives in the system and in a specified time is equal to the number of tasks which have been serviced. So for example, if 10 tasks arrives to the system, say in 10 seconds. The server may take, say, only 0.5 seconds for one system, for one task, 1 second for another task, 1.5 seconds for the third task, and so on. But if the total time taken by all the tasks to arrive and all the tasks to get serviced, where individual tasks may take different time, but all the tasks have been serviced, then this system is said to be a steady state system. So for this purpose, in fact, the Little's law is the most important law which governs this particular response time and the throughput. The Little's law states that the mean number of tasks in a system is equal to the mean response time multiplied by the arrival rate. So here in this, this actually have become a very complex definition. The mean number of tasks in a system can be defined as the time which is the total accumulated time for a particular operation to be done. Or say if there are 10 tasks, then what is the total accumulated time for these 10 tasks? Divided by the time observed. The time observed is the time, which means that what is the time which has been taken to have been in the system and then before getting the response. As you can see from the next step, that is the mean response time, is the time, accumulated time, divided by the number of tasks. This means that in the total time, how many tasks have been completed. So this in fact relates or gives rise to the information regarding the throughput. The last parameter over here is the arrival rate, which is usually represented by the Greek letters lambda, and it is equal to the number of tasks divided by the time observed. If we look into these three definitions, we can combine them together to find the expression which is known as the Little's law. And this expression, as you can see, that this expression is the expression for the mean number of tasks that may be completed in a specified time. And this expression can be written as we have defined earlier, the expression for mean number of tasks can be defined as the time accumulated divided by the time observed. As you can see from this slide, if we rewrite this previous expression, it can be written as the time accumulated multiplying number of tasks, and which means that if this particular first, the expression which is given on the left hand side can be rewritten as by multiplying and dividing by the number of tasks, then this expression is, that is the time accumulated divided by the number of tasks divided by the time observed. As we have defined above, the time accumulated divided by the number of tasks is equal to the mean response time, and the number of tasks divided by the time observed is equal to the arrival rate. So this in fact gives rise to the proof of the expression which we mentioned earlier. So now with this much introduction about the Little's queuing theory and the time which is used to, or how we can measure the performance of an I/O system in terms of the response time, the mean number of tasks which can be covered up, we can well understand that what is the relationship between the response time and the throughput. For this purpose, we can go through certain practical examples which I will be giving you in the form of home assignments from your notes, and that you will be getting from your actual notebooks which are provided to you with this course. Now, after talking about the performance of the input-output system, the performance of the processor, and the performance of the memories. From the memory design, what is the response time, what is the overall performance of the system. We can talk about the performance of the overall system, which consists of both the processors as well as input-output devices. It also includes the memory system, and it also includes if some different types of processors are interconnected, then it includes for parallel processing and for multiple processing, it also includes other processors also. We will, considering these things, we will now talk about the overall performance of the system. This overall performance of the system and how this performance can be enhanced. It can be determined by using the well-known law introduced by Professor Amdahl's, and it is known as the Amdahl's law. As you can see from this slide, the Amdahl's law states that if we want to improve the performance of a system, then the speed up of the system, it depends upon not necessarily enhancement of the performance in all components and in all aspects, that is in both hardware, software and everything. Rather, we can enhance the performance of a small fraction, and this will in fact enhance the performance of overall system to a large extent, and we can get the speed up of in the system. The example for this can be that if we have to execute a program, and let us suppose that this program has got some integer simple arithmetic instructions like addition, subtraction, etc., and some logical instructions like AND operation, OR operation, etc. But at the same time, say it has got some floating point instructions also. We know that the floating point instructions, we will discuss about the floating point instructions in some more details at the later time, but at this stage you can in fact consider it as if it is an instruction which may take say 10 times to 15 times more time as compared to integer type instruction. In order to make it further simple, we can say that if a system is having say if a program has got simple arithmetic instructions like add, subtract, etc., and some multiply or divide instructions. As you already have studied at your undergraduate level, that the multiply or divide instructions are usually executed by implementing some algorithm, and it usually takes 10 to 15 times more time as compared to the simple arithmetic instructions like add, subtract, etc. So now if in a program, let us suppose there are 100 instructions for simple addition, subtraction of the integer number, but there are 20 instructions for multiply and divide. Now and we want to speed up the overall performance of the system. There are two choices, rather we can say that there are three choices. One is that we increase the performance of redesign the system or redesign our software so that the execution time for simple arithmetic instruction is enhanced, and at the same time the execution time, we make some changes in the algorithm for multiplication also, and the execution time for the multiply or divide instruction is also reduced, and this can give us a speed up in the overall performance of the system. Alternative is we take a decision that either to improve the performance of those parts of the system which are responsible for only integer type of instructions, or improve the performance or speed up the operations or performance of the system which is responsible only for multiply or divide instruction. Now that if we are given a choice, You know, you have already studied this thing that for addition or subtraction instruction, you have got different types of techniques available. Simple method is the ripple adder. Then instead of ripple adder, you can use carry look ahead adder or carry safe adder, etc. And this way you know this thing that the system performance for addition subtraction instructions can be improved by, say, by a factor of 2% or 2 times. Whereas if we make some changes in the algorithm for multiplication or division, and if it becomes possible that the performance is increased or this has been speeded up by a factor of 10, that is, instead of taking 0.5 seconds to execute multiply instructions, let us suppose now it takes only 0.05 seconds to execute the multiply instructions. So the Amdahl's law states that, as you can see from this slide, the Amdahl's law states that the speed up due to the enhancement is equal to the execution time without enhancement divided by the execution time with enhancement. Now, as we discussed in the second lecture, that performance and execution time has inverse relationship. Therefore, we can say that the speed up is equal to the performance with enhancement divided by the performance without enhancement. So this shows that now if we have to calculate the speed up, then the speed up can be calculated by calculating the execution time with enhancement and the execution time without enhancement. By dividing these two, we can find out the overall speed up after enhancement. So for this purpose, let us see this next expression. In this next expression, you can see that what is the new execution time? New execution time means the execution time after the enhancement or with enhancement. So this execution time with enhancement is basically equal to the execution time without enhancement of those parts which has not been enhanced. As with respect to the previous example, if total program takes say 10 microseconds to execute, which takes in which the simple arithmetic instructions are 70% of the total program, and the multiply and divide instructions are only 30% of the total instructions. And if the performance of the multiplier or divider is only improved, we will consider the fraction. Enhanced fraction is 1, which is in fact the corresponding to the fraction of time, which is corresponding to the taken by the multiply instruction. So therefore, from this point of view, as you can see from this slide, execution time in this particular case for enhanced section is, we have to determine first of all the execution time for the old system without enhancement, which is equal to 1 minus the fraction enhanced, because fraction enhanced we have to take up in the second part. Therefore, the total new execution time is the execution time required for those portion which has not been enhanced, which is equal to the old execution time, plus the execution time for those portions which has been enhanced, and that is equal to the fraction divided by the speed up of the enhancement multiplied by old execution time. So considering this, as you can see from the next expression, if we rearrange this expression, you can see that the speed up is equal to execution time without enhancement divided by the execution time with enhancement. So this means that if we move the execution time given on the left hand side of the first expression and then the inverse of the remaining part of the expression on the right hand side, the new expression will be, as you can see from the expression shown here on the screen, you can see that it is equal to 1 divided by 1 minus fraction enhanced plus fraction enhanced divided by speed up enhanced. Now, knowing this expression, we can find out the overall speed up in the whole performance. And based on this, you can calculate the new performance. Now, we will take a practical example of enhancement made in a circuit or in a program by making enhancement only in a fraction of the program. We will consider an example where we assume that a program consists of both the integer type instructions as well as the floating point instructions. However, you can say that the floating point instructions are taking 10% of the total time taken by the whole program, whereas the remaining program takes 90% of the time. Now, if we make some arrangements to improve or speed up the floating point section of the data path or of the design, and we make some arrangements to enhance its performance such that it is speeded up by a factor of 2, then we can find out the overall performance enhancement and the speed up in the system by calculating the new execution time vis-a-vis the old execution time, and then we can find out the overall performance enhancement. For this purpose, let us have a look on your screen. You can see that we can say new execution time is equal to the old execution time multiplied by 1 minus fraction enhanced. The fraction enhanced is 10%, so therefore it is equal to 0.9 plus the fraction enhanced, which is equal to 0.1, divided by the speed up. The speed up, as it is mentioned here, that it is 2 times faster now, therefore its speed up is equal to 2. This gives us the total value of the new time after enhancement is equal to 0.95 times the old execution time, or the execution time without enhancement. By rearranging this expression, we can say that the speed up after making an enhancement in only 10% of the total time, the overall performance enhancement is equal to 1 divided by 0.95, which is equal to 1.053 times. So this shows that speed up is approximately 5.3 times, 3% as compared to the original value of this. So now with this much discussion on to the Amdahl's law, I will like to conclude today's session by looking into what we have studied in this first part of 3 lectures. Because this first part is basically covering almost all topics which have been discussed in chapter 1 of your book. We started our discussion with the basic introduction to what is a computer, what are different parts of a computer. We studied this, found this thing that a computer consists of 3 major components, 3 major sections, that is the input-output devices, the memory system, and the processing section, all being interconnected by a system of buses. Then we talked about the difference between the computer architecture and computer organization. Having got introduction to this, then we discussed the technology trends. And we found that the technology trends, in fact, made it possible to change the food chain from its normal routine to a new routine. The normal food chain, as we know, is that a big fish always eats small fish. But the food chain of the computer is opposite. Today's small pieces, they have in fact eaten up the old big massive computers of costing millions of dollars, and now presently the same performance can be achieved by these new systems by massively interconnecting these processors, parallel processing systems, or different interconnecting systems, wherein we share the memories also, we share the processors also, and we enhance the performance. I also gave you a brief history of the computer development, and then we moved on to the serious part of our discussion, which is relating to the introduction to the computer design cycle. In the computer design cycle, we talked about how we start from the basic specifications of the requirement to be achieved by a system. We then convert these basic requirements from its specifications, which are usually given in a simple English. We convert this into a language, into a form which is providing us a hardware-based implementation of the requirements. And that is being done by converting this information to a register transfer level and dividing this whole design into two major sections, that is the data path and the control path. The data path, in fact, covers the register transfer section, where from the input registers, the data is moved to the output register, and during this transfer of data from input to the output, the required operation is performed onto the given data. However, in order to perform these operations, some control circuitry is needed, and that control circuitry is developed by using different techniques such as finite state machine approach or microprogramming approach. Then after making this discussion onto the design cycle, we studied over here that we cannot design the whole system in one go and we can say that it will start working. Rather, we take different steps, such as this design, which is initially made at the elementary level by using describing it in some register transfer language. We pass on this through a simulator and we analyze its performance, its behavior, and if some improvements or modifications are needed, we suggest that or make those, and then ultimately, once a designer is satisfied, then he converts this information into a form which is ready for converting this into the implementing this onto the hardware. And this form is basically one where we move from this one layer of design, that is the data circuit design for data path at the logic level to the circuit level. However, this is the hardware section, but this whole hardware design is relying, or it is based onto what is the instruction set architecture. And we said that in the beginning, we said that the instruction set architecture is in fact the central is at the central location in the overall processor design methodologies. So considering this, we discussed the importance of the instruction set architecture, how it affects, and we will further be talking in details in the effect of different design aspects of the instruction set architecture starting from the fourth lecture and onward. However, over here then we talked about the performance, technology trends, and cost. And ultimately, at the end, I discussed with you two different discuss with you what is the performance enhancement methodologies for the I/O systems and what are the performance enhancement at the overall system level. For the overall system level, for the I/O system level, we considered or discussed the queuing theory, which is also known as the Little's queuing theory, and we measured the overall response time, the time observed and the time accumulated, and all those things we took into consideration, and we determined the overall time for for the I/O processing. Then at the end, I talked about the Amdahl's law, which is in fact used to find out the speed up in the overall performance based on the fraction enhancement. That is, instead of enhancing the performance of each and every part of the hardware, as well as of the software, we can take a decision in the beginning. We can model our system, we can divide it into sections, and we can make some modifications in different parts of the system and make the enhancements over here. This is basically a step towards the quantitative design, and that was our theme on in this lecture as well as in the previous lecture. So with this much introduction about the design and the quantitative approaches for the performance enhancement of the system, we will stop our discussion over here, and next time, inshallah, we will take into consideration the instruction set architecture, what are different parameters of the instruction set architecture, and how we can, taking into consideration the instruction set architecture, how we can proceed for the designs of the data paths for single cycle, multiple cycle, or pipeline architecture. With all these discussions, I stop here today. I say you Khuda Hafiz and see you next time. Thank you very much.